For the remainder of this session, we're going to be having a discussion on some introductory concepts just to get us all in the same place. So the first thing we want to talk about is computers. We're going to be working in Linux system on computers. You guys are all IT majors, so I assume that you are very fluent in these concepts. Online people, in text chat, please give me, as simply as you can, tell me what is a computer. Go. Looking for any definition you want to give as to what is a computer. If for some reason you're unsure and you're getting an answer from somewhere else, be sure to acknowledge that. So if you're getting it from some online site or something else, you should briefly acknowledge that in your posting. Okay, so I'm starting to see it is a machine. Okay, it is a mechanical, an electronic machine in particular. It's not mechanical these days. It does computations, it has software and hardware, it stores and sends data, it does mathematical equations. Dean says whether human, mechanical, or electronic. So broadly, the word computer in earlier times could be applied to a person. Someone who did computations could be called a computer, someone who did computations. There were mechanical devices to do these, but when we use the word today, we mean an electronic device. Compares, calculates. Justin says a machine with a GUI. I presume that means graphical user interface. Computer does not have to have a graphical user interface. Some do, some do not. Device that takes data and turns it into information. Okay, I'm not crazy about that last suggestion. Information is a human concept. Computers do not understand information. Computers process data. Quinn says, does what human programs it to do. Yes, okay. So to these days, a computer typically is a programmable device. Not always, but most commonly what we think of as a computer is a general purpose device that you can load different software into it to do different things. Hugo says manipulate data and information. Again, I suggest a computer processes data, not information. Information requires data to be put into context. It requires understanding, and that is something that a computer cannot do. That distinction between data and information is typically not well understood. It's kind of blurred because we have some very sophisticated data processing applications that are designed to mimic human thinking processes, and so some of the things that a computer does looks like things that a person would do with information. Dean says like AI. Yes, we can get AI. You can go to AI and say, write me a 1,000-word essay on security administration of Linux systems or something like that, and it'll produce a whole bunch of words that look like a person who understood the concept might put together. In some cases, not a very good job. In other cases, quite a reasonable job. But we should understand that a computer does not actually understand anything at all. I call a computer a bit shuffling machine. Certain bits go in, there is circuitry that produces certain bits in response. And the computer itself has no understanding of what those bits mean. It just takes a bit pattern and produces some other bit pattern. We call it information technology because it is technology that assists the human information process. Computers exist to help people make decisions, do work, do useful things. Okay, so let's go back, and we mentioned hardware and software. Let me check what I've got here. Yeah, so let's go back to that. So we can make a distinction between the hardware and the software, and there's lots of different ways to do this, but I'm going to do it like this. So we've got, let me draw hardware at the bottom and then draw some software on top of that. So we'll make a distinction between these two things. was quite clunky. Okay, so the hardware, what do we mean by hardware? We mean the physical equipment that makes up the computer. And someone had mentioned graphical user interface. Okay, so it gives us a clue. So what do we find in the hardware? What are the essential components of the hardware? Suggestions, please. Okay, so different types of computers, these we might find. There may be a motherboard. What's on the motherboard? Okay, so Stephen has given us CPU and RAM. Okay, so let's talk about those two things. So here I'll just type it quicker. Okay, so we have a CPU, Central Processing Unit. And we have RAM. I'm just going to generalize that to memory because there's different kinds of memory. There's RAM, there's ROM. So we've got CPU and we've got memory. And we can actually map the memory to the software that is above. So let me move that. Although it's hardware, I'll drag it if I can. Okay, how to use this thing. I'm going to pull it off to the side and say within the hardware that is the memory, we have the abstract interpretation of software. What is the purpose of the CPU? To do calculations, do computations. Okay, so the CPU, this is what I call the bit shuffling part of the computer. A CPU takes data in from memory, and we can write data out from the CPU back to memory. There are lots of different kinds of memory. The CPU actually has its own memory locations. There's a small number, typically 16 or 32 or 64, something like that, a very small number of memory locations called registers. They are extremely fast because they're kind of baked into the hardware of the CPU, but it's a very small number of them. And then there are different layers of memory leading out to things like the RAM, where we have a huge amount of it, but it is relatively slow compared to the registers, the cache, and some other things. So we have a small amount of very fast memory. We have a very large amount of relatively slower memory, but we won't get into those distinctions. And I'm going to add another arrow here from the CPU to itself. Okay, so at a really high level, we can load data into the CPU, we can take data out of the CPU, or we can transform the data that is within the CPU. So for example, if we wanted to add two numbers together and take the result to a third place, so let's say we want to write something in code, we might write C equals A plus B. We would load A into a register, we might load B into another register. We have an instruction to add two registers together and put them into a third register, and then we'd write that third register out to memory. In order to know what the CPU should be doing, there is another input. So this first input is data. So there's data in and data out. And then there is instructions that go in. That's another input to the CPU. So the CPU gets an instruction word telling it what to do. Some of the instructions are to load data, some are to write data, some are to transform it. We can do things like increment, just add one to a register value. There are branch instructions that tell us instead of just going in sequence, instructions, typically you just take instructions from memory, one location after the other in sequence. Sometimes we want to skip over some, sometimes we want to go backwards in order to create a loop. There are conditional branch instructions, so we do some kind of test and then decide whether or not to branch. So if we were going to write a loop where we're going to do something some number of times, we would go through a sequence of instructions, one of which might increment or decrement a value, then we would test whether it's equal to 0. If it is, then we would, or if it's not 0, we would go backwards and do the loop again and again, and at some point we would not go backwards, we'd continue on with the following instructions. Let's think now about what is in this software. Okay, so we've got data going in and out of the CPU. So in the software, we've got instructions and we've got data. Typically, we're going to have, in a general purpose computer, we're going to have a layer of memory, and I'll just work on the side here. So the lowest layer is going to be the operating system. And then above that, let me draw that like this. Above the operating system, we're then going to have some number of applications, which I'm drawing as rectangles, different size and shapes because they have different content, different amounts of memory. Some applications require others, so we could put an application on maybe one that spans 2 others like this. We have applications on top of applications. Applications can be loaded and unloaded dynamically, so you might start to run a new program or application. And when you finish, you might get rid of it, say I'm done with that. So things can come and go. Different applications can request more memory to be allocated, or they can free up memory, so the amount of memory used by an application. Typically, the instruction part tends to be static. The data part tends to be dynamic. So as you start an application, we load the instructions, and some of the instructions request a certain amount of memory to be allocated for the application. At some point, we may give that back. We may stop using it. And the memory allocations can change as the application goes. Adam says, isn't the kernel the lowest level? Yes, within the operating system, we can then make further. We're going to talk about operating systems in more detail in a moment. Okay, so that's a really high level view of what's going on. Now, where does the data come from? We're missing an essential set of components here. What else do we have other than what I've shown? Dean says I/O. Okay, yes, so input and output. What are some types of inputs and types of outputs? So what do we generally call the devices that are providing the data in and out? Okay, so we've got mouse, keyboard, touch screen, other things like that for inputs from users. We've got the screen as an output. We've got printers. We've got networking in both directions. Okay, so we generally call these peripherals. Peripherals meaning on the edge. So I'm just going to put here without naming them. We've got lots of things providing data in and things providing data out. Some of those inputs are human-oriented. So you've got a person who's interacting with the computer, typing things on the keyboard, looking at the screen, using all sorts of other input-output devices. Some of the data is going to or from other devices, other computers, networking devices, all sorts of different things. So we've got networking, essential component that of modern computers. These days, a computer with no networking is not very useful at all. A standalone device, this is something not much more complicated than a handheld calculator, for those of you who remember those. If you can't move data into and out of the computer and make it part of a network system of computers, then it probably isn't doing anything terribly useful the way that we do things today. Justin says motion detectors, heat sensors. Computer is just a chip that takes a feed and stores it. Okay, so we are some computers very sophisticated. You look at your own laptop or something like that. Others very, very simple. You take a modern car, has several dozen computers doing all sorts of different things. Some of them very simple, doing maybe only one thing. Today we have computers in kitchen appliances and other things like that. So very limited range of functions might be implemented in dedicated hardware, not even with software, or the software may be very straightforward. Others very sophisticated, designed to interact as part of multi-computer systems using distributed processing and so on. So lots and lots of different ways to implement this. Okay, that's a good starting point to talk about computers. Okay, so one of the components of what we had in the software layer is the operating system. So in the memory of the computer, let's just call it memory generally, we have the data to be processed, and then we have the instructions, the actual software. And there is layer upon layer upon layer of software, and the lowest layer just above the hardware is the operating system, which in turn we can break down into further layers. We mentioned the kernel and some other things. Let's talk about, what does the operating system do? Just give me a word or phrase for some of the things that are done by the operating system. Question is, what does the operating system do? Okay, it says manage system resources including permissions. Justin says ties in all the peripheries. Manages I/O, yes. Security, perhaps. Actually, I'll say yes on that. That's a pretty good place to put that. Even says bridges software and hardware together. Okay, yeah, certainly bridges higher level applications sit on top of the operating system. So if I was to draw that diagram again, I would have the hardware here. I would have an operating system layer here as the first software layer. And then on top of that, I would have applications we had earlier, maybe application on top of another application and so on. And all those applications are working through the operating system. Okay, it says an abstraction layer. Yeah, I won't get into that term. I think that's probably not helpful here. Manager processes queries. I don't think the operating system processes queries. I think you're thinking of databases there. Certainly one of the things that it is doing is resource management. There is a finite amount of RAM in the system, a finite amount of resource, but particular RAM, and applications are requesting RAM. So an application may say, I want 1,000 memory locations, or I want 1 million, or whatever, so they request a certain amount of memory. And we've only got so much. What happens when all the applications that are running in total request more memory than the system has? Adam says suspended. Adam, what is suspended? Gulam says the system slows down. Why does it slow down? Quinn says it lags or it crashes. Hopefully it does not crash. That would not be good. Okay, so a couple people talking about virtual memory and paging. Okay, yes. So what happens here is the operating system can take a certain chunk of memory and send it to the hard disk or equivalent, some storage peripheral, where it is stored, and then it can free up that amount of memory to be used by an application that needs it. When that memory is needed, it needs to be brought back in from the hard disk. So we need to swap out some other memory, bring this amount back in from the hard disk, and make it available back to its application. So the memory can be temporarily kind of moved from RAM out to disk and back again. That is a relatively slow process. The RAM, although it's slower than the cache, which is slower than the registers, it's a lot faster than the disk or the extra whatever that storage is. So there is a delay in doing that. And The operating systems typically are fairly clever about predicting when the memory is going to be needed, and if the memory can be brought back in before it's needed again, or the application doesn't mind waiting for that to happen, it's not an issue. Where it becomes a problem is what we call a page fault, where an application wants access to memory which is currently on the disk, and then the application has to be suspended to wait for that chunk to be brought back in. That's called a page fault. It involves a time delay, and if you get a lot of time delays like that, the system then becomes very slow. And if you've got constant page faults, if you've got, for example, two large applications competing for a lot of memory, and we're spending a lot of time swapping things in and out of disk and a lot of time actually doing work, the system can get to the point where it seems to be frozen. If that happens, some systems, there's a light on the hard disk drive, typically on desktop computers, not laptops, but sometimes you can see there's a little LED that is blinking when there's activity to the disk, and you may notice that LED is completely lit all the time, meaning the disk is constantly moving data in and out. At that point, the system is probably very, very slow or appears to be frozen. So one of the things the operating system is doing is managing access to a finite pool of memory and using this virtual technique to make it appear that we have more memory than we really do, at the expense of occasionally having to wait for memory to be moved in and out. Okay, so memory management is one thing. Another thing the operating system is doing is scheduling. And I say scheduling because I speak Australian English. You might say scheduling. This is allocating access to the CPU. And for simplicity, to understand this concept, let's just assume there is one CPU, one core CPU. So let's go back, before we had multi-core, let's go back 20 years. So there's one CPU that is handling processing of instructions. You've got multiple applications and the operating system itself. So everything above the hardware layer here, all of these things want to be executing instructions. Only one instruction can be executed at a time. So the operating system has to determine which application gets access to the CPU and when to give it to another one. There's all sorts of ways to manage this. An application will get to a point where it's waiting for something. So it may be waiting for something to be read in from a peripheral, or something to arrive on the network, or a user interaction. So there are kind of natural points where an application is suspended, and that's a good time to bring another application in to give it a turn. But you may have two applications that are just doing a lot of computations, and you don't want one to get exclusive control for a long time, and then the others appear to be doing nothing. So the operating system, they use some clever techniques to give each application kind of a, let's say very broadly, a fair subset or a fair portion of the available instruction time. And ideally, we are not overloading the system, or not even getting close to anything like 100% utilization. We want the CPU to be idle a lot of the time in order that the system then appears to be running quite quickly. Once you get anything like, let's say, approaching 75% utilization on average, then you've probably got a lot of peaks where you're running at 100%, and at that point you have applications that are simply waiting for their turn, not waiting for something else to happen. But if the system's not terribly busy, the operating system does a job of giving each application chunks of access to the CPU, and from a human perspective, everything seems to be running along. And it seems that multiple things are happening. We've got different applications running. So right now I've got a bunch of tabs open in my browser. I've also got a spreadsheet open, my calculator, and some other things, and my calendar app and other things running. It looks like there's a lot of things happening at the same time. In reality, only one thing is happening at a time, but the operating system is able to schedule access to the CPU in order to give this illusion of multitasking. It gets more complicated when you get to multi-core CPUs, because you can have obviously two different applications running on two separate CPUs, But sometimes one application wants access to multiple CPUs if it's got multiple threads, depending on how the application's been coded. So this becomes then a multi-dimensional problem. We're not going to get into that level of complexity. Okay, so we talked about resource management. We talked about scheduling. Someone mentioned security. There are some security things that are managed by the operating system. For example, an application is given a certain amount of memory. If it attempts to access a memory location outside of what it has been allocated, the operating system will prevent that. That will typically cause a fault, which may lead to a crash in the application. Application should be coded not to do that, so there's typically a programming error. There are certain parts of memory, certain things that are mapped to memory, which are read-only, so you can only read from them. Other parts that are write-only, like display. If you're writing to the graphics, you don't read what is currently at a pixel, you simply write to it. So it also manages what privileges in terms of read or write access an application has. We talked earlier about the distinction between instructions and data. There was a point where there was attempts made to distinguish between those two. So memory locations in chunks could be marked as read-only because they were instructions to be read, not data to be written to. That effort was not terribly successful because there were ways around it. The idea was to make it so that an application couldn't modify its own code unless you really wanted that, but typically you don't, so that you couldn't have some malware or something like that take control of an application and make it do something different. The attempt was to do that at a very low hardware level where the operating system could enforce that, and those efforts failed. That technology is not terribly widespread anymore because it just didn't work very well. But those are some of the things going on in the operating system. Oh, and another thing, so we talked about layers within the operating system. Let's erase this. So within the operating system itself, someone mentioned the kernel. So the kernel is the essential part. Kernel with a K is the essential part of the operating system, and then there are pieces. We'll talk about operating system structure perhaps a little later, but typically what we see today is a modular approach where the kernel is kind of the essential part that's always there, and then you have modules that you can load, similar to what we saw earlier with applications. So you can load modules into the operating system, and you can unload them so these things can come and go. So there's different pieces that we find doing different things. It is time dynamic, so it can change from time to time. One of the types of things we find in the operating system, I'll put here as D, is device drivers, DD for device drivers. And this is software that handles access to or from peripherals. So I'll just draw here a couple of arrows. So this might be, for example, something to do with networking, where it is monitoring for data incoming to the system and then also sending data out of the system. And this software interacts very closely with the hardware. Typically, if you're writing an application, you don't want to be monitoring individual bits going on at the hardware level because it's different hardware looks different depending on what's there. So we have multiple layers of abstraction where your software simply says, I want to write to the network. I want to write to a particular network device or something like that. And then we have multiple layers going down. The device drivers are fairly low-level pieces of the operating system that handle devices directly. So that's another thing going on in the operating system. Okay, that gives us a good idea of what's going on there.